Subscribe to the channel so you don't miss out on any of these videos. The universe is vast, ancient, and filled with mysteries that challenge our understanding of existence. Among the most fascinating and elusive enigmas are population 3 stars, the first generation of stars that ever illuminated the cosmos. Imagine a time when the universe was dark, silent, and devoid of the complex elements that make up everything we see today, including ourselves. Now, picture the very first lights flickering into existence, stars that burned with a purity and intensity we can only dream of. These weren't ordinary stars. They were the architects of cosmic evolution, the primordial forges that created the first seeds of life's building blocks. But here's the catch. Despite their monumental role, not a single population 3 star has ever been observed. What happened to them? Why are they so crucial? And how do they hold the key to understanding the origins of everything? The story of population 3 stars is not just about stargazing. It's about unraveling the earliest chapters of the universe itself. Today, we'll dive deep into this cosmic mystery, piecing together what scientists know, theorize, and still question. To understand population 3 stars, we need to travel back in time, billions of years before Earth existed, before galaxies swirled and planets formed, before even the chemical elements we take for granted existed. After the Big Bang, the universe was an expanding sea of simple particles, hydrogen, helium, and traces of lithium. These were the primordial elements, the firstborn of cosmic nucleosynthesis. There were no metals, no carbon, no oxygen, nothing complex enough to form the rich diversity of matter we see today. The universe was chemically pristine, a blank slate waiting for its first brushstrokes. Population 3 stars were those brushstrokes. These stars formed from the pure hydrogen and helium left over from the Big Bang, without any heavier elements to influence their structure or evolution. Unlike the stars we see today, which are composed of a mix of elements forged by previous generations, population 3 stars were unpolluted. This purity is what makes them so unique and fascinating to scientists. Their formation, life cycle, and ultimate demise shaped the universe in ways that set the stage for everything that followed. So, how did these stars come into being? In the early universe, slight fluctuations in the density of matter caused regions of gas to collapse under their own gravity. These collapsing pockets of gas heated up, eventually igniting nuclear fusion, the process that powers stars. But because the gas was so pure, the dynamics of star formation were vastly different from what we observe today. Modern stars rely on elements like carbon and oxygen to cool down the gas and allow it to condense more efficiently. Population 3 stars, lacking these cooling agents, likely grew to be extraordinarily massive, with estimates suggesting they could have ranged from tens to hundreds of times the mass of our Sun. This immense size came with consequences. Massive stars burned through their fuel much more quickly than smaller ones. Population 3 stars were no exception. They lived fast and died young, exploding as supernovae or even more dramatic hypernovae within a few million years, a blink of an eye on cosmic timescales. These explosive deaths scattered the first heavy elements, metals, in astronomical terms, into the surrounding universe. This process, known as metal enrichment, was crucial. It seeded the cosmos with the ingredients needed for the next generations of stars, planets, and eventually, life. But here's the twist. Despite their critical role, population 3 stars have eluded direct observation. Their ephemeral nature and the immense distances involved make detecting them incredibly challenging. Instead, scientists piece together their existence through indirect evidence. For example, the chemical composition of ancient stars in the Milky Way's halo suggests the presence of earlier generations of stars that contributed to the metal content of the galaxy. Similarly, observations of distant galaxies and the light from quasars provide clues about the conditions of the early universe, hinting at the legacy of population 3 stars. Advancements in technology, like the James Webb Space Telescope, bring us closer to uncovering these ancient stars. Webb's ability to peer into the farthest reaches of the universe, essentially looking back in time, offers a tantalizing opportunity to glimpse the era when population 3 stars first shone. If we can detect their signatures, it would be like finding a missing page in the history of the universe, a page that explains how the cosmos transformed from a simple expanse of gas into the complex tapestry we see today. But what makes the mystery of population 3 stars even more compelling is the way they challenge our understanding of cosmic evolution. Theoretical models suggest they played a key role in reionizing the universe, a pivotal phase that ended the so-called cosmic dark ages. This reionization allowed light to travel freely through space, shaping the universe's structure and laying the groundwork for galaxy formation. Without population 3 stars, the universe as we know it might look entirely different, or might not exist at all. And yet, questions remain. Were these stars truly as massive as models predict? Did they form in isolation, or were they part of primitive star clusters? What was their impact on the formation of black holes, particularly the supermassive black holes that sit at the centers of galaxies? Could they hold clues about dark matter, the mysterious substance that makes up most of the universe's mass but remains invisible and elusive? These unanswered questions keep scientists searching, theorizing, and pushing the boundaries of what we know. The hunt for population 3 stars is not just a quest for understanding our cosmic origins. It's a testament to humanity's insatiable curiosity and our drive to explore the unknown. The story of population 3 stars reminds us that even in the face of vast uncertainties, the universe leaves traces, subtle clues that, when pieced together, can illuminate the darkest corners of existence. And as we continue to develop new tools and techniques, we move closer to uncovering the secrets of these first stars, the cosmic pioneers that lit the way for everything that followed. The legacy of population 3 stars is not just confined to the early universe. Their influence permeates the cosmos we see today. By forging the first heavy elements, these stars laid the foundation for the creation of everything complex in the universe. Without them, there would be no carbon to form the basis of life, no iron to build planets, and no oxygen for us to breathe. The very atoms in our bodies owe their existence to these ancient stars, which transformed the simple elements of the Big Bang into the rich palette of the periodic table. One of the most profound contributions of population 3 stars was their role in creating the conditions necessary for the next generations of stars. When these massive stars exploded as supernovae, they released shockwaves that compressed nearby gas clouds, triggering the formation of new stars. These subsequent generations, known as population 2 stars, inherited the metals forged by their predecessors. This process of enrichment and recycling continued, eventually leading to the stars we see today, classified as population 1. But let's not rush ahead. To fully appreciate the importance of population 3 stars, we need to delve deeper into the physics of their formation and life cycle. The absence of metals in these stars fundamentally altered their behavior. Metals are excellent radiators of energy, helping gas clouds cool down and fragment into smaller pieces during star formation. Without metals, the cooling process was far less efficient, resulting in larger, hotter stars. These stars burned at temperatures far exceeding those of modern stars, emitting intense ultraviolet radiation that influenced their surroundings in profound ways. This ultraviolet radiation was critical for a phenomenon known as cosmic reionization. After the Big Bang, the universe was initially hot and ionized, with particles freely zipping around. But as the universe expanded and cooled, it entered a phase called the cosmic dark ages, during which neutral hydrogen dominated and light was trapped. The intense radiation from population 3 stars reionized this hydrogen, freeing the photons and allowing light to travel through space once again. This event marked a turning point in the history of the universe, paving the way for the large-scale structures we observe today. However, this process wasn't uniform. The reionization of the universe was patchy and complex, with some regions becoming transparent to light earlier than others. This uneven reionization is a topic of active research, as it provides valuable insights into the distribution of matter and the behavior of the first stars. Understanding this process requires advanced simulations and observations, and it's an area where technology like the James Webb Space Telescope shines. Despite the theoretical frameworks and indirect evidence, there remains a lingering question: why haven't we found direct evidence of population 3 stars? Their existence is supported by a wealth of indirect data, but their fleeting nature and extreme conditions make them elusive targets. Scientists are looking for telltale signs, such as the chemical fingerprints they may have left in the oldest stars still alive today. These ancient stars, known as metal-poor stars, carry the chemical signatures of the environment in which they formed. By studying their composition, researchers hope to infer the characteristics of the first stars. Moreover, astronomers are searching for population 3 stars in the most distant galaxies, where light has traveled billions of years to reach us. This light acts as a time machine, allowing us to see the universe as it was shortly after the Big Bang. In these ancient galaxies, the first stars may have left subtle imprints in the spectrum of light. Detecting these signals requires incredibly sensitive instruments and sophisticated analytical techniques, but the potential rewards are immense. Confirming the existence of population 3 stars would be a groundbreaking achievement, rewriting our understanding of cosmic history. The quest to uncover the secrets of population 3 stars also intersects with other profound mysteries of the universe. For instance, their massive size and short lifespans may have contributed to the formation of the first black holes. When these stars collapsed at the end of their lives, they could have created black holes that later merged and grew into the supermassive black holes we see at the centers of galaxies today. This idea is still speculative, but it offers an intriguing link between the earliest stars and some of the most enigmatic objects in the universe. Additionally, population 3 stars may hold clues about the nature of dark matter. Dark matter doesn't interact with light, making it invisible to telescopes, but it exerts a gravitational influence on ordinary matter. Some theories suggest that dark matter played a crucial role in the formation of the first stars, acting as a scaffolding around which gas could accumulate and collapse. Studying population 3 stars could provide indirect evidence about the properties of dark matter, shedding light on one of the most profound mysteries in modern physics. The more we learn about population 3 stars, the more we realize how interconnected their story is with the broader narrative of the universe. These stars weren't just the first lights in the cosmos, they were the catalysts for transformation, turning a simple, homogeneous universe into the complex, dynamic one we inhabit today. Their influence extends across time and space, touching everything from the formation of galaxies to the emergence of life. But the story of population 3 stars is far from complete. As technology advances and our understanding deepens, new questions arise. Were these stars truly as massive and short-lived as current models suggest, or is there a more nuanced picture waiting to be discovered? Could there still be remnants of population 3 stars hidden in the farthest reaches of the universe, waiting to be found? And what can they teach us about the ultimate fate of the cosmos? These questions remind us that the universe is not a solved puzzle but an ever-evolving mystery. Every discovery about population 3 stars adds a new piece to the picture, but the full image remains tantalizingly out of reach. And that's the beauty of science. It's a journey, not a destination. The quest to understand the first stars is a testament to human curiosity and our relentless drive to explore the unknown. The search for population 3 stars continues to inspire new methodologies and cutting-edge technology, each aimed at unraveling their elusive secrets. To truly comprehend their nature, scientists are pushing the boundaries of what's possible in observational astronomy. Space telescopes like the James Webb Space Telescope, JWST, have opened unprecedented windows into the distant universe, probing regions where these primordial stars may have ignited over 13 billion years ago. The JWST, in particular, is a game-changer. Its infrared capabilities allow it to peer through vast stretches of intergalactic gas and dust, detecting faint signals from the first billion years of cosmic history. If population 3 stars existed in these distant epochs, their signatures might emerge in the spectra of early galaxies. Scientists are meticulously analyzing these spectral lines, looking for telltale signs of the extreme ultraviolet radiation emitted by these massive, metal-free stars. While direct evidence remains elusive, the JWST is providing invaluable data that could bring us closer than ever to confirming their existence. But why are these spectral signatures so important? The light from population 3 stars would be unlike anything observed from modern stars. With no metals to moderate their nuclear fusion processes, these stars burned at extraordinarily high temperatures, producing copious amounts of ultraviolet radiation. This radiation would ionize the surrounding gas, creating distinct emission lines in the spectrum of light from their host galaxies. Identifying these lines would not only confirm the presence of population 3 stars but also provide insights into their properties, such as mass, temperature, and lifespan. While space telescopes focus on distant galaxies, researchers on Earth are also contributing to the search for population 3 stars. Ground-based observatories equipped with advanced spectrographs are scanning the skies for metal-poor stars in our own galaxy. These ancient stars, often found in the halo of the Milky Way, are believed to be second-generation stars that formed from the remnants of population 3 supernovae. By studying their chemical compositions, scientists can infer the characteristics of the stars that preceded them. The chemical analysis of these metal-poor stars has already yielded fascinating results. Some of these stars exhibit extremely low levels of heavy elements, suggesting that they were enriched by only a single population 3 supernova. This chemical fingerprinting allows researchers to reconstruct the conditions in which these ancient stars formed, providing indirect evidence of the first generation of stars. The more we learn about these metal-poor stars, the closer we come to piecing together the puzzle of population 3 stars. Theoretical models also play a crucial role in this quest. Simulations of the early universe, run on some of the world's most powerful supercomputers, help scientists understand how population 3 stars might have formed and evolved. These models incorporate complex physics, including the interplay between gravity, radiation, and gas dynamics, to recreate the conditions of the primordial cosmos. By comparing the predictions of these models with observational data, researchers can refine their understanding of the first stars. One of the most intriguing predictions from these models is the possibility that population 3 stars could have been part of binary or even multiple star systems. If true, this would have significant implications for their evolution and eventual demise. Interactions between stars in a binary system can lead to phenomena like mass transfer, which might affect their lifespans and the type of supernova they produce. Detecting evidence of such systems would add a new layer of complexity to our understanding of the first stars. As we deepen our exploration, we must also grapple with the broader implications of population 3 stars for the universe's evolution. Their role in reionization, for example, is a topic of intense debate. While it's clear that these stars contributed significantly to the reionization process, they were not the sole players. Other sources, such as early galaxies and black holes, also emitted ultraviolet radiation that helped reionize the universe. Determining the relative contributions of these sources is a key challenge in cosmology. Moreover, the study of population 3 stars intersects with questions about the formation of galaxies. These stars likely played a critical role in shaping the first galaxies, providing the energy and heavy elements needed for their growth. Understanding this connection is essential for building a comprehensive picture of how the universe transitioned from a featureless expanse of gas to a complex web of galaxies, stars, and planets. The impact of population 3 stars extends even further, touching on the origins of life itself. The heavy elements they created, such as carbon, nitrogen, and oxygen, are essential for the chemistry of life. Without these elements, complex molecules like DNA and proteins could not form. By studying population 3 stars, we are essentially tracing the cosmic roots of our own existence. It's a humbling thought. The atoms that make up our bodies were forged in the fiery hearts of ancient stars that existed long before Earth was even a possibility. Yet, despite their importance, population 3 stars remain shrouded in mystery. Their fleeting existence and extreme conditions make them a challenging target for study. But it's this very challenge that drives scientists to innovate and explore. The quest to understand these stars is more than just a scientific endeavor. It's a testament to humanity's insatiable curiosity and our desire to connect with the universe. The search for population 3 stars is also a reminder of how much we have yet to learn. Each discovery raises new questions, pushing the boundaries of our knowledge and inspiring the next generation of scientists. It's a journey that requires patience, perseverance, and a willingness to embrace the unknown. And while the answers may not come easily, the pursuit itself is a profound expression of our shared humanity. As we continue to study the cosmos, the story of population 3 stars will undoubtedly evolve. New technologies and techniques will bring us closer to uncovering their secrets, shedding light on one of the most fascinating chapters in the history of the universe. And through it all, we'll be reminded of the extraordinary power of science to illuminate the darkness and reveal the wonders of the cosmos. The allure of population 3 stars is not just about their physical properties but also the profound questions they raise about the origins and destiny of the cosmos. These stars are a cosmic bridge, linking the fiery beginnings of the universe to the intricate tapestry we observe today. Their story is a reminder that the universe, in all its vastness, is a continuum of transformation, a constant interplay between destruction and creation. One of the most captivating aspects of population 3 stars is their role as harbingers of the first black holes. Given their massive sizes, many of these stars likely ended their lives in spectacular supernovae, leaving behind black holes as remnants. These primordial black holes may have been the seeds for the supermassive black holes we observe in the centers of galaxies today. Understanding this connection is a major focus of modern astrophysics, as it ties the formation of the first stars to the evolution of large-scale cosmic structures. The study of these black hole seeds is intertwined with a broader mystery. How did supermassive black holes form so quickly in the early universe? Observations of quasars, galaxies with actively feeding supermassive black holes, show that some of these black holes had already reached billions of solar masses just a few 100 million years after the Big Bang. This rapid growth is difficult to explain under conventional models, but population 3 stars might hold the key. If these stars formed in dense clusters and produced multiple black holes, interactions within these clusters could have led to the rapid merging and growth of black holes. This potential link between population 3 stars and supermassive black holes is a vivid example of how the first stars influenced cosmic evolution on multiple scales. Their light not only reionized the universe but also laid the groundwork for the formation of galaxies, clusters, and the vast structures that define the cosmic web. Every element of the universe we see today can trace its lineage back to these pioneering stars. But for all their significance, direct evidence of population 3 stars remains tantalizingly out of reach. Scientists often describe them as ghosts of the universe, whose presence is inferred through indirect observations. This indirect approach involves piecing together clues from a variety of sources, from the chemical fingerprints of ancient stars in the Milky Way to the spectral lines of distant galaxies. Each clue adds a piece to the puzzle, bringing us closer to a complete picture. One of the most exciting avenues for discovery lies in the study of gamma-ray bursts, GRBs. These bursts of high-energy radiation are among the most powerful events in the universe, often linked to the deaths of massive stars. If a GRB were to be observed originating from a metal-free environment, it could serve as compelling evidence for a population 3 star. Current and future observatories are on high alert for such events, which would provide a rare glimpse into the final moments of these ancient stars. The interplay between observation and theory is another hallmark of this field. Theoretical models predict that population 3 stars should have formed in small clusters, where their intense radiation could influence the formation of neighboring stars. Observing such clusters would not only confirm the existence of population 3 stars, but also provide insights into their formation mechanisms. However, detecting these clusters requires instruments with incredible sensitivity and resolution, capabilities that are only now becoming available. The quest for population 3 stars also intersects with the study of dark matter. These stars likely formed in regions where dark matter was concentrated, as its gravitational pull would have helped gather the gas needed for star formation. Understanding this relationship could shed light on the nature of dark matter itself, one of the most profound mysteries in modern science. By studying the environments where population 3 stars formed, scientists hope to uncover new clues about this elusive substance. As we delve deeper into this cosmic mystery, it becomes clear that the story of population 3 stars is not just about the past, it's about the future. Their legacy is written in the stars that followed, in the galaxies that grew, and in the planets that formed. They are the ancestors of everything we know, from the elements in our bodies to the light that illuminates the night sky. And yet, for all their significance, they remain a symbol of the universe's enduring mystery. The first stars were born in a time of darkness, igniting a cosmic dawn that forever changed the universe. Their light traveled across billions of years, carrying with it the story of creation itself. To study these stars is to gaze into the heart of the cosmos, to seek answers to questions as old as time. As we look to the future, the search for population 3 stars will continue to inspire and challenge us. New missions, such as the Nancy Grace Roman Space Telescope and upcoming ground-based observatories, promise to push the boundaries of what we can observe. These instruments will probe deeper into the cosmos than ever before, offering new opportunities to uncover the secrets of the first stars. But beyond the technology and data, the quest for population 3 stars is a profoundly human endeavor. It is a testament to our innate curiosity, our desire to understand where we come from and how we fit into the universe. In seeking the light of these ancient stars, we are not just exploring the cosmos, we are exploring ourselves, our origins, and our place in the grand cosmic story. The story of population 3 stars is far from over. As we stand on the cusp of new discoveries, we are reminded of the infinite possibilities that the universe holds. Each step forward brings us closer to the answers we seek, illuminating the path with the light of the first stars. And so, the journey continues, guided by the faint echoes of a cosmic dawn that still resonates across the vast expanse of space and time. The journey to uncover the secrets of population 3 stars reflects humanity's broader quest to understand the universe itself. These primordial stars are more than just physical phenomena. They are symbols of a time when the cosmos transitioned from simplicity to complexity, from darkness to light. To explore their nature is to peer into the very beginnings of time and space, unraveling the story of how the universe as we know it came to be. One of the most tantalizing questions surrounding population 3 stars is how they influenced the formation of cosmic structures. These stars were not solitary beacons of light but rather integral components of the universe's early evolution. Their immense energy output likely influenced the behavior of the surrounding intergalactic medium, creating ripples that shaped the formation of subsequent stars and galaxies. This phenomenon is often referred to as feedback, a process where the radiation and winds from massive stars alter their environment. In the case of population 3 stars, their feedback was likely so intense that it cleared away surrounding gas, halting further star formation in some regions while triggering it in others. This dual role makes them both creators and destroyers, illustrating the complex interplay between stars and their environments. Feedback mechanisms are a key focus of theoretical models, which aim to simulate the conditions of the early universe. These models suggest that population 3 stars may have existed in small groups or clusters, where their collective radiation created bubbles of ionized gas. These bubbles would expand over time, influencing nearby regions and potentially creating the first proto-galaxies. By studying these processes, scientists hope to understand how the large-scale structures of the universe, galaxies, clusters, and filaments, emerged from the chaotic aftermath of the Big Bang. Another intriguing aspect of population 3 stars is their potential role in forming the first molecules. While the universe's primordial composition was dominated by hydrogen and helium, small amounts of other elements like deuterium and lithium were also present. These elements, combined with the intense radiation from population 3 stars, could have facilitated the formation of simple molecules such as molecular hydrogen, H2. These molecules would have played a crucial role in cooling the gas, enabling the formation of subsequent generations of stars. The chemical legacy of population 3 stars extends to their explosive deaths. When these massive stars exhausted their nuclear fuel, they likely ended their lives as supernovae or hypernovae, scattering newly forged elements across the cosmos. These events seeded the universe with the first heavy elements, setting the stage for the chemical diversity we observe today. Every atom of carbon in your body, every molecule of oxygen you breathe, can trace its origins back to these cosmic pioneers. The impact of population 3 supernovae was not limited to their immediate surroundings. The heavy elements they produced would have mixed with the intergalactic medium, enriching it with the building blocks of future stars and planets. This process, known as chemical enrichment, created a cosmic feedback loop where each generation of stars contributed to the formation of the next. By studying the chemical compositions of ancient stars, scientists can trace this enrichment process, piecing together the history of the universe's first few billion years. The remnants of population 3 stars may also hold clues to their existence. If these stars left behind black holes, neutron stars, or other exotic objects, these remnants could provide indirect evidence of their properties. Observing these objects in the modern universe is a challenge, but their discovery would offer a window into the conditions of the early cosmos. For example, the detection of a metal-free neutron star would strongly suggest that it originated from a population 3 progenitor. The search for these remnants is closely tied to the study of gravitational waves. When massive objects like black holes or neutron stars merge, they produce ripples in the fabric of spacetime that can be detected by instruments like LIGO and Virgo. If a merger involving population 3 remnants were observed, it would provide a wealth of information about their masses, spins, and other properties. Such an event would be a groundbreaking discovery, offering direct evidence of the first star's existence. Despite these advances, the mystery of population 3 stars remains unsolved. Their transient nature and extreme conditions make them elusive targets, even for the most advanced telescopes. Yet, this very elusiveness adds to their allure, challenging us to push the boundaries of science and technology. The search for these stars is a testament to the resilience and ingenuity of the human spirit, a reminder that some of the universe's greatest mysteries are also its most rewarding. As we stand on the brink of new discoveries, the story of population 3 stars continues to inspire. Their light, though long extinguished, still illuminates the path forward, guiding us toward a deeper understanding of the cosmos. Each new piece of evidence brings us closer to answering the fundamental questions of our existence. Where did we come from? How did the universe begin? And what is our place in the grand cosmic story? In many ways, the search for population 3 stars is a journey through time. It is an exploration of the universe's earliest moments, a quest to uncover the origins of everything we see around us. From the smallest atom to the largest galaxy, the legacy of these stars is written across the cosmos. Their story is our story, a testament to the interconnectedness of all things. As scientists continue to probe the depths of space, the echoes of the first stars serve as a reminder of the universe's boundless wonder. Each discovery brings us closer to understanding the mysteries of the cosmos, revealing a universe that is as complex as it is beautiful. And while the search for population 3 stars may be challenging, it is also profoundly rewarding, offering a glimpse into the origins of light, life, and everything in between. The quest is far from over, and the future holds limitless possibilities. With new technologies and innovative approaches, the secrets of population 3 stars may finally be revealed. Until then, their story remains a beacon of curiosity and exploration, a testament to the enduring power of human ingenuity. The enduring allure of population 3 stars lies not just in their role as the first sources of light, but in the profound implications they carry for understanding the very fabric of the universe. These stars, born from a universe devoid of metals, represent a time when the cosmos was both simpler and infinitely more mysterious. Their existence poses questions that span the realms of physics, chemistry, cosmology, and philosophy, each layer deepening our appreciation for the complexity of the universe. One of the most fascinating aspects of population 3 stars is their influence on subsequent star formation. By reionizing the surrounding regions and dispersing heavy elements, these stars essentially reset their environments. This effect would have varied depending on the size of the star cluster, the density of the surrounding medium, and the distribution of dark matter. Each of these variables adds nuance to our understanding of how galaxies and star systems formed in the aftermath of the Big Bang. Moreover, these primordial stars may have had a hand in shaping the dynamics of dark matter itself. Simulations suggest that population 3 stars likely formed in halos of dark matter, which acted as gravitational wells for the gas clouds that eventually gave rise to these stars. The intense radiation from the stars could have heated the surrounding gas, preventing it from collapsing back into the dark matter halo. This interplay might have affected the distribution of dark matter on both small and large scales, influencing the overall structure of the universe. The study of population 3 stars also intersects with the field of cosmic magnetism. While the early universe was largely unmagnetized, the turbulent environments around these massive stars could have generated the first magnetic fields. These fields, though weak, might have played a role in shaping the behavior of gas and dust in the early universe, influencing the formation of galaxies and clusters. Tracing the origins of these magnetic fields could provide valuable insights into the physical conditions that prevailed during this epoch. Another critical avenue of research involves the relationship between population 3 stars and the cosmic microwave background, CMB. The CMB is the faint afterglow of the Big Bang, carrying imprints of the universe's earliest moments. The reionization caused by population 3 stars would have left subtle signals in the CMB, such as distortions in its polarization patterns. By analyzing these signals, scientists can gain indirect evidence of the presence and properties of these ancient stars. This connection between the first stars and the CMB highlights the interdisciplinary nature of astrophysics. Population 3 stars are not just a topic of interest for stellar physicists, they are a cornerstone of cosmology, touching on themes as diverse as galaxy formation, chemical evolution, and even the search for extraterrestrial life. Understanding these stars requires a collaborative effort that spans observational astronomy, theoretical modeling, and experimental physics. The search for population 3 stars also has implications for the study of planetary systems. While these stars themselves would have been inhospitable to life, their chemical contributions laid the groundwork for the formation of planets, and eventually life. The elements they produced, carbon, oxygen, nitrogen, and others, are the building blocks of biology. By studying the environments in which these elements were first created, scientists hope to uncover clues about the conditions necessary for life to emerge. In this context, population 3 stars can be seen as cosmic alchemists, transforming the simplest elements into the complex chemistry that defines our world. Their explosive death scattered these elements across the universe, enriching future generations of stars and planets. This process of enrichment is a key theme in astrophysics, linking the lives of individual stars to the broader narrative of cosmic evolution. The study of population 3 stars also raises philosophical questions about the nature of the universe. These stars represent a time when the cosmos was radically different from what we see today, a time when light was scarce, and the universe was dominated by darkness and simplicity. Their existence challenges us to think about the nature of change and continuity, about how the past shapes the present and the future. This philosophical dimension is particularly poignant when considering the observational challenges associated with these stars. The light of population 3 stars has long since faded, and their remnants are scattered across the cosmos. Yet, their influence is everywhere, embedded in the very fabric of the universe. To study them is to look for traces of a vanished world, to seek out the echoes of a time when the universe was young. As technology advances, the prospects for discovering these ancient stars grow brighter. Next-generation telescopes, such as the Extremely Large Telescope, ELT, and the Square Kilometre Array, SKA, promise to revolutionize our ability to observe the early universe. These instruments will have the sensitivity and resolution needed to detect the faint signatures of population 3 stars, bringing us closer than ever to solving this cosmic mystery. Yet, even as we look forward to these discoveries, the story of population 3 stars serves as a reminder of the limits of human knowledge. For all our advances, there are still aspects of the universe that remain beyond our grasp. These stars, with their ephemeral existence and profound impact, symbolize the interplay between the known and the unknown, between what we can observe and what we can only imagine. This interplay is what makes the study of population 3 stars so compelling. They are not just objects of scientific inquiry. They are symbols of the universe's capacity for wonder and surprise. Their light, though long extinguished, continues to illuminate our understanding of the cosmos, guiding us toward deeper insights and greater questions. As we continue this journey, we are reminded that the universe is not a static entity but a dynamic, evolving system. Population 3 stars are a testament to this dynamism, to the constant interplay of creation and destruction that defines the cosmos. Their story is a chapter in the larger narrative of the universe, a story that we are still writing, one discovery at a time. The story of population 3 stars is intricately woven into the fabric of cosmic evolution, illustrating the symbiotic relationship between the first light of the universe and the subsequent formations that arose from their ashes. Despite their transient existence, these stars left an indelible imprint on the cosmos, shaping the trajectories of galaxies, enriching the interstellar medium, and influencing the formation of later generations of stars and planetary systems. As we delve deeper into their significance, the narrative becomes even more captivating. One of the most profound legacies of Population 3 stars lies in their contribution to cosmic nucleosynthesis. Prior to their formation, the universe contained only hydrogen, helium, and trace amounts of lithium, products of the Big Bang. These stars, through their nuclear fusion processes, synthesized the first heavy elements, or metals, in astronomical terms. This initial enrichment laid the groundwork for the chemical diversity we observe in the universe today. The heavier elements forged in their cores would eventually become the raw materials for everything from rocky planets to complex biological molecules. The process of metal enrichment initiated by Population 3 stars was anything but uniform. Their immense energy output and supernova explosions created turbulent environments, dispersing elements unevenly across the cosmos. This inhomogeneous distribution of metals would have profound implications for the formation of the first galaxies. Regions enriched with heavier elements would cool and collapse more efficiently, giving rise to stars with lower masses and longer lifespans, while metal-poor regions continued to host massive, short-lived stars. This patchwork of chemical environments added a layer of complexity to the early universe, influencing the distribution and characteristics of galaxies we see today. Furthermore, Population 3 stars played a critical role in the reionization of the universe, a pivotal epoch in cosmic history. In the aftermath of the Big Bang, the universe entered a period known as the Dark Ages, during which neutral hydrogen dominated, and light from early objects was obscured. The intense ultraviolet radiation emitted by Population 3 stars ionized this neutral hydrogen, gradually clearing the cosmic fog and allowing light to travel freely. This reionization process transformed the universe from an opaque to a transparent state, enabling the formation of large-scale structures and the development of the observable universe. Reionization, however, was not a uniform process. The clustered nature of Population 3 star formation meant that ionized bubbles formed around these stars, gradually expanding and merging with others. This patchy reionization created a mosaic-like structure in the early universe, with regions of ionized hydrogen interspersed with neutral pockets. Studying these patterns provides crucial insights into the properties of Population 3 stars and the mechanisms driving their formation. Another fascinating aspect of these stars is their relationship with black holes. The most massive Population 3 stars likely ended their lives in direct collapse black holes, bypassing the supernova phase entirely. These early black holes may have served as seeds for the formation of supermassive black holes observed at the centers of galaxies. The rapid growth of these black holes in the early universe remains a topic of active research, with Population 3 stars providing a critical piece of the puzzle. The connection between Population 3 stars and dark matter also warrants attention. As mentioned earlier, these stars formed within halos of dark matter, which acted as gravitational wells for primordial gas. The interplay between the radiation emitted by these stars and the surrounding dark matter could have influenced the density and distribution of dark matter on both local and cosmic scales. Understanding this relationship is crucial for unraveling the mysteries of dark matter, a substance that makes up the majority of the universe's mass yet remains elusive to direct detection. In addition to their role in cosmic structure formation, Population 3 stars also offer insights into the physics of extreme environments. Their immense masses and high temperatures push the limits of nuclear fusion, creating conditions vastly different from those in later generation stars. By studying these conditions, scientists can test and refine models of stellar physics, gaining a deeper understanding of the fundamental processes that govern the behavior of stars. Despite their profound impact, direct observational evidence of Population 3 stars remains elusive. Their light, redshifted by the expansion of the universe, is challenging to detect with current instruments. However, their signatures may be imprinted in the spectra of distant galaxies and quasars. For instance, the presence of certain ionized elements, or the absence of metallic lines can provide indirect evidence of their existence. These spectral clues are like fingerprints, offering tantalizing hints of the first stars without revealing their full identities. Upcoming telescopes and missions promise to shed new light on these ancient objects. The James Webb Space Telescope, JWST, with its unprecedented sensitivity to infrared wavelengths, is expected to detect the faint glow of early galaxies and star clusters, potentially uncovering the signatures of population 3 stars. Similarly, the Square Kilometre Array, SK, will revolutionize our understanding of the early universe by mapping the distribution of neutral hydrogen during the epoch of reionization. These advancements bring us closer to answering some of the most profound questions about the origins of light and structure in the cosmos. As we push the boundaries of observation and theory, the quest to understand population 3 stars also invites us to reflect on our place in the universe. These stars, as the first luminous objects, mark the beginning of a chain of events that ultimately led to the formation of our solar system, our planet, and life itself. They are a reminder of the interconnectedness of cosmic phenomena, of how the smallest interactions in the early universe can have far-reaching consequences billions of years later. In this sense, the study of population 3 stars is not just about uncovering the past, it is about understanding the processes that continue to shape the universe today. From the distribution of galaxies to the chemical makeup of stars and planets, their influence is everywhere, a testament to the enduring legacy of the first light. The journey to uncover the secrets of population 3 stars is far from over. Each discovery adds a new layer of complexity to their story, challenging our assumptions and expanding our understanding of the cosmos. In their brief but brilliant existence, these stars set the stage for everything that followed, illuminating not just the early universe but the pathways of our own exploration. Their light may have faded, but their story continues to inspire, a beacon guiding us toward the unknown. The tale of population 3 stars continues to unravel in the quiet hum of laboratories, the precision of telescopes, and the ever-growing data pools from simulations. Their role in shaping everything from galactic dynamics to the chemical pathways of life demands exploration at levels both broad and meticulous. One of the most pressing questions about population 3 stars is their life cycle. How did these giants, composed purely of hydrogen and helium, burn through their nuclear fuel, and how did they meet their end? Their enormous masses, often ranging between tens to hundreds of solar masses, mean they were short-lived by stellar standards, existing for mere millions of years. Their rapid life cycle contrasts sharply with stars like our Sun, which can persist for billions of years. These ephemeral lifespans meant population 3 stars worked as cosmic engines, injecting energy, radiation, and metals into the interstellar medium in astonishingly short timescales. Their death throes were particularly dramatic. Unlike later generation stars, which end in more predictable supernova explosions, the end stages of population 3 stars are thought to be diverse and extreme. Some of the smaller population 3 stars likely exploded as supernovae, ejecting heavy elements into space and enriching nearby gas clouds. But for the most massive stars, their collapse would have been so powerful that they might bypass the supernova phase entirely, collapsing directly into black holes. These black holes, as mentioned earlier, are theorized to be seeds of supermassive black holes seen in modern galaxies. Another intriguing possibility is that population 3 stars were the origin of parent-stability supernovae, a rare and highly energetic explosion. In such a supernova, the intense radiation pressure in the core of a massive star creates pairs of electrons and positrons, reducing the outward pressure and causing the star to collapse. This process can result in the complete obliteration of the star, leaving behind no remnant, no black hole, no neutron star, just an expanding shell of enriched material. These explosions are among the most luminous and energetic events in the universe, capable of enriching vast regions of space with heavy elements. The existence of such diverse end states underscores the complexity of these stars' influence on their environment. Their deaths didn't just enrich the surrounding medium, they also shaped the dynamics of their host halos. The explosive release of energy from supernovae could have disrupted gas clouds, preventing further star formation temporarily. On the other hand, the enrichment of these regions with metals lowered the cooling threshold, enabling the subsequent formation of smaller, longer-lived stars. This dual role as both disruptors and facilitators highlights the intricate feedback processes initiated by population 3 stars. While population 3 stars themselves may no longer exist, their descendants are all around us. Stars formed in the enriched regions left behind by population 3 explosions are often referred to as population 2 stars. These second-generation stars, while still metal-poor compared to modern stars, carry the chemical fingerprints of their predecessors. By studying these ancient population 2 stars in the Milky Way and other galaxies, astronomers can piece together the characteristics of population 3 stars indirectly. The ratios of certain elements, such as carbon, oxygen, and iron, act as chemical signatures, providing clues about the nuclear processes that occurred in the first stars. Interestingly, not all population 3 stars may have enriched their surroundings equally. Some models suggest that low-mass population 3 stars, if they formed at all, could have lived much longer, potentially surviving to the present day. These elusive stars, sometimes called fossil stars, are a holy grail for astronomers. Finding even one such star would provide direct evidence of the first generation of stellar objects, offering an unprecedented window into the early universe. Despite extensive searches, no unambiguous population 3 star has been found, suggesting that if they do exist, they are exceedingly rare. Beyond their immediate environments, population 3 stars also influence the large-scale structure of the universe. Their intense radiation likely contributed to the formation of ionized regions around nascent galaxies, creating the first cosmic web. This web of interconnected galaxies and dark matter filaments is the backbone of the universe's structure. By shaping the ionization and chemical states of their surroundings, population 3 stars indirectly influence the formation and evolution of this web. The study of these connections helps astronomers understand how the universe transitioned from a homogeneous state to its current rich tapestry of galaxies and voids. The challenge of studying population 3 stars extends beyond their physical properties. Their existence forces scientists to grapple with fundamental questions about the origins of complexity in the universe. How did such massive objects form in an environment with no metals? What role did turbulence, magnetic fields, and dark matter play in their formation? Each question opens up new avenues of exploration, blending theoretical physics, computational simulations, and observational astronomy. Theoretical models of population 3 stars rely heavily on simulations, as direct observations remain out of reach. These simulations recreate the conditions of the early universe, following the cooling and collapse of gas clouds within dark matter halos. Advances in computational power have enabled increasingly detailed simulations, capturing the interplay of gravity, radiation, and hydrodynamics in unprecedented detail. These models suggest that population 3 star formation was not a solitary event but occurred in clusters, with multiple stars forming within a single halo. The interactions between these stars, through their radiation, winds, and supernovae, add layers of complexity to the story. Observationally, the hunt for population 3 stars focuses on their indirect signatures. Distant galaxies and quasars, visible at extreme redshifts, carry the imprint of these ancient stars in their light. By analyzing the spectra of these objects, astronomers can identify the chemical compositions of their host environments. For instance, the absence of heavy elements, or the presence of certain ionization states can hint at the influence of population 3 stars. These observations, though challenging, provide crucial evidence to test and refine theoretical models. The next generation of telescopes promises to revolutionize our understanding of population 3 stars. The James Webb Space Telescope, JWST, is expected to detect the faint glow of the earliest galaxies, potentially revealing clusters of population 3 stars. The 30-meter telescope, TMT, and the European Extremely Large Telescope, ELT, will offer even greater sensitivity and resolution, enabling detailed studies of the chemical and dynamical properties of early galaxies. These advancements bring us closer to answering some of the most profound questions about the universe's origins. As we look to the future, the study of population 3 stars reminds us of the interconnectedness of cosmic phenomena. These ancient giants, despite their fleeting existence, laid the groundwork for everything that followed. They were the first beacons of light, the first forges of complexity, and the first harbingers of the rich and diverse universe we see today. Their legacy is written in the stars, in the galaxies, and in the very atoms that make up our world. The search for population 3 stars is not just about understanding the past, it is about connecting the dots of cosmic history, bridging the gap between the Big Bang and the universe we know. In their story, we find echoes of our own, an odyssey of creation, transformation, and discovery. Their light may have faded, but their influence endures, a timeless testament to the power of beginnings. As we continue to peel back the layers of the universe's past, we gain more insight into the powerful and mysterious forces that shape the cosmos. The study of population 3 stars is not merely a pursuit of cosmic curiosity but also one that holds the potential to redefine our understanding of star formation, galaxy evolution, and the very nature of the universe itself. To further grasp the significance of population 3 stars, it is essential to consider how their formation and evolution compare to the processes seen in later generations of stars. While the first generation of stars emerged from pristine hydrogen and helium, later generations, including population 2 and 3 stars, were enriched with heavier elements created through earlier stellar processes. This enrichment, known as chemical evolution, plays a crucial role in the ability of stars to form planets and support complex chemistry. Without the first stars to generate these elements through nuclear fusion and supernovae, the universe would have remained a sterile and inhospitable place for life as we know it. The metals produced by population 3 stars were essential for the formation of the next generation of stars, including those capable of forming planets. Elements such as carbon, oxygen, and nitrogen are critical for the existence of life, but their creation was impossible without the deaths of the first stars. The chain of events initiated by these stars, through their explosive deaths or the formation of black holes, ultimately enriched the gas clouds that later gave birth to population 2 stars. These stars would eventually give rise to the first galaxies and the subsequent universe that we can observe today. As we attempt to reconstruct the evolutionary timeline of stars, we must consider that our understanding of population 3 stars is still largely theoretical. Many of the details of their formation, evolution, and demise remain elusive because we are observing a universe that is in many ways opaque to our current observational capabilities. The extreme distances involved, combined with the faintness of early galaxies and stars, make it incredibly difficult to detect direct evidence of these first-generation stars. Yet, astronomers have made remarkable progress in piecing together the puzzle through a combination of observational techniques and advanced simulations. Simulations of population 3 star formation have been invaluable tools in predicting the conditions under which these stars would have formed. For example, simulations suggest that these stars were born in massive clouds of gas and dust that were heated by the radiation from the first supernovae and cosmic microwave background (CMB) radiation. The cooling of these clouds would have allowed the gas to collapse under gravity, eventually forming the first stars. However, the unique chemical composition of these clouds, lacking metals, would have had profound effects on the star formation process. The absence of heavier elements meant that these stars could not cool as efficiently as later stars, potentially leading to the formation of extremely massive and hot stars that burn through their fuel much faster. One of the most exciting aspects of population 3 stars is their potential to help explain the formation of the earliest black holes. As mentioned earlier, the most massive population 3 stars may have collapsed into black holes instead of undergoing supernovae. These black holes, while short-lived in terms of stellar lifetimes, could have grown exponentially by accreting gas from their surroundings. This growth process is thought to be a key factor in the formation of supermassive black holes, which are found at the centers of most large galaxies, including our own Milky Way. By understanding the role of population 3 stars in the formation of black holes, astronomers are unlocking secrets about the early universe and its evolution. It's not just the direct contributions of population 3 stars to cosmic evolution that fascinates scientists. Their study also provides valuable insights into the broader processes that govern the formation of galaxies, clusters, and the large-scale structure of the universe. The intense radiation and winds produced by these stars likely had a profound effect on the intergalactic medium, affecting the distribution of matter and energy across the cosmos. This process, known as reionization, is thought to have occurred around 1 billion years after the Big Bang, when the universe transitioned from being opaque to transparent to light. Population 3 stars played a critical role in this process, helping to ionize the hydrogen gas that permeated the early universe, paving the way for the formation of galaxies and larger cosmic structures. Another area of intense focus is the relationship between population 3 stars and dark matter. Dark matter, the mysterious and invisible substance that makes up a significant portion of the universe's mass, is thought to have played an integral role in the formation of the first stars. Simulations suggest that the gravitational influence of dark matter halos may have provided the necessary structure and conditions for the formation of population 3 stars. In turn, these stars may have influenced the distribution of dark matter, as their radiation could have affected the behavior of gas and dark matter in the early universe. By studying population 3 stars and their interactions with dark matter, scientists are inching closer to understanding one of the greatest mysteries in modern astrophysics. One intriguing aspect of this discussion is the connection between population 3 stars and the phenomenon of cosmic inflation. Cosmic inflation refers to the incredibly rapid expansion of the universe in the first fraction of a second after the Big Bang. This expansion is thought to have set the stage for the formation of the first galaxies and stars. By studying the cosmic background radiation and the ways in which it was affected by the formation of the first stars, scientists are gaining deeper insights into the connections between early star formation, the large-scale structure of the universe, and the very origins of cosmic inflation itself. As we continue to develop more sophisticated tools and techniques for studying the universe, the discovery of population 3 stars and their contributions to the cosmos remains one of the great frontiers of modern astrophysics. Whether through new telescopes, more advanced simulations, or groundbreaking theoretical models, the search for answers to the questions surrounding these enigmatic stars will shape our understanding of the universe for decades to come. The next-generation space observatories, like the James Webb Space Telescope and the upcoming extremely large telescopes, hold the promise of unlocking new mysteries and shedding light on the events that took place billions of years ago. Population 3 stars may no longer shine in the sky, but their impact is written into the very fabric of the universe. They were the first beacons of light in a dark and chaotic cosmos, and their existence marked the beginning of a new era in the universe's history. As we look deeper into the past, through both simulations and observations, we may one day uncover even more about these incredible stars and the mysteries they hold. The story of population 3 stars is far from over, and with every discovery, we get closer to understanding the profound significance of the first light in the universe. As we venture deeper into the study of population 3 stars, it becomes clear that these stars were more than just the first lights in the universe. They were the catalysts for a cosmic transformation that set the stage for the creation of everything we know today: galaxies, stars, planets, and even life itself. To truly appreciate their importance, we must explore the lasting impact of these stars on the universe's chemistry and structure. The core elements of our existence, carbon, oxygen, and nitrogen, did not simply appear in the early universe. They were forged in the hearts of stars, and the first generation of stars, the population 3 stars, played a pivotal role in this process. By the time these stars reached the end of their lifespans, they had transformed their surrounding environments, leaving behind a legacy of heavy elements. These elements would go on to seed the next generation of stars, eventually allowing the universe to evolve into the rich, complex cosmos we observe today. To fully understand the role of population 3 stars in cosmic chemistry, it's essential to explore the concept of nucleosynthesis. Nucleosynthesis is the process by which stars create elements through nuclear fusion. In population 3 stars, this process was limited to the lightest elements, hydrogen and helium. However, as these stars aged and died, they exploded as supernovae, sending out shockwaves that triggered the formation of new elements. These supernovae were the factories that produced the first heavy elements, which would later form the building blocks for everything in the universe. These early explosions were also responsible for enriching the intergalactic medium with the elements necessary for the formation of future generations of stars. The fusion products created by population 3 stars were essential for the emergence of population 2 stars, which were capable of forming planets. The birth of these second-generation stars marked a significant shift in the evolution of the universe. For the first time, stars could form in a way that would allow the creation of planetary systems. Without the nucleosynthesis carried out by population 3 stars, planets, and by extension, life, might never have had the chance to exist. It's fascinating to consider how population 3 stars might have differed from the stars we see today. As we mentioned earlier, these stars were composed almost entirely of hydrogen and helium, with only trace amounts of heavier elements. This gave them a distinct set of characteristics that set them apart from later stars. For one, they were incredibly massive and hot, much larger than most stars in the present-day universe. Their high mass meant that they burned through their fuel at an extraordinarily rapid rate, often only lasting a few million years, far shorter than the lifespans of the stars we see today. This short-lived nature made them rare, but their impact was profound. In terms of their size, population 3 stars were believed to have masses hundreds of times that of the Sun. This meant that they had a much higher core temperature, which allowed them to fuse elements much faster. Because of these extreme temperatures, these stars likely reached temperatures of over 100 million degrees Celsius, enabling them to initiate fusion processes that are not common in less massive stars. The radiation and heat emitted by these stars would have been immense, affecting the surrounding gas and even accelerating the processes of galaxy formation. Another key aspect of population 3 stars is the possibility that they could have formed differently from stars in later generations. The absence of metals in the early universe meant that these stars were not able to cool as efficiently as their successors. Metals act as cooling agents in stellar formation, as they allow gas to cool and collapse into denser regions, facilitating the formation of stars. Without metals, the gas that formed population 3 stars was much hotter and denser, making it more likely for these stars to form in larger clusters or even as multiple stars within a single system. The rapid rate at which population 3 stars burned through their fuel also had important implications for their eventual deaths. Most of these stars would have ended their lives in catastrophic supernova explosions, spreading their newly created heavy elements throughout the universe. These explosions were not only essential for creating the building blocks for new stars and planets, but also for seeding the universe with the essential materials for life. The energy released in these supernovae was so intense that it triggered the formation of black holes, further influencing the structure and dynamics of the early universe. The question of how population 3 stars died remains an area of intense study. While many of these stars would have ended their lives in supernovae, some may have collapsed directly into black holes, bypassing the supernova explosion altogether. These black holes, formed in the deaths of the first stars, might have grown over time to become the supermassive black holes that reside at the centers of galaxies today. This connection between population 3 stars and black hole formation is one of the most intriguing aspects of modern cosmology. As we study the remnants of the first stars, we also gain insight into the processes that led to the formation of galaxies. The intense radiation and wind from population 3 stars likely played a crucial role in the formation of the earliest galaxies. These stars could have helped to heat and ionize the surrounding gas, allowing it to collapse and form the first structures in the universe. Without population 3 stars, it's difficult to imagine how galaxies could have emerged in the early universe. Observing the light from population 3 stars, however, is a challenge. These stars are located far beyond the reach of current telescopes, making it difficult to detect their light directly. Instead, astronomers rely on indirect methods to study them. By looking at the faint glow from distant galaxies and analyzing the chemical composition of the gas in these galaxies, scientists can infer the presence of population 3 stars. The James Webb Space Telescope, which is poised to launch in the coming years, may provide new insights into these stars by observing the infrared light emitted by the first galaxies and stars. Despite the difficulty of observing population 3 stars directly, researchers have made significant strides in simulating their formation and behavior. These simulations, combined with observations of distant galaxies and supernovae, are helping to paint a clearer picture of what the first stars were like. These stars may have been incredibly hot, massive, and short-lived, but their influence on the universe was far-reaching and profound. The elements they created in their cores and released in their explosive deaths provided the raw materials for the stars and planets that followed, setting the stage for the formation of the cosmos as we know it. Through their violent births and dramatic deaths, Population 3 stars left an indelible mark on the universe, influencing everything from the formation of galaxies to the creation of life-supporting elements. As we continue to search for answers about these first stars, we are not just uncovering the secrets of the early universe, we are also learning more about our place in the cosmos. The mysteries of Population 3 stars will continue to inspire future generations of astronomers, as we seek to unlock the secrets of the universe's very first light. The search for the remnants of Population 3 stars has become one of the most exciting frontiers in modern astronomy. Though these stars themselves may no longer exist, the legacy they left behind continues to shape our understanding of the cosmos. The chemical fingerprints left by their explosions, as well as the radiation they emitted, are imprinted on the earliest galaxies and the gas clouds that form in the vastness of space. By studying these traces, we can uncover more details about the conditions in the early universe and the processes that led to the formation of the first galaxies and star systems. One of the most powerful tools in this pursuit is spectroscopy. By analyzing the light from distant galaxies, astronomers can break it down into its component wavelengths and detect the unique absorption lines created by different elements. These absorption lines can tell us a great deal about the composition of the gas and stars within those galaxies. In particular, they provide clues about the presence of the heavy elements that Population 3 stars produced. Since Population 3 stars were made mostly of hydrogen and helium, their death would have resulted in the first significant contributions of heavier elements such as carbon, oxygen, and iron to the surrounding environment. The distribution of these elements in distant galaxies offers important information about the timeline of star formation and the enrichment of the intergalactic medium. The James Webb Space Telescope, JWST, which is currently set to launch, holds the promise of revolutionizing our understanding of the first stars. Unlike the Hubble Space Telescope, which primarily observes invisible light, JWST is designed to look at the universe in the infrared spectrum. This is significant because the light from the first stars and galaxies is stretched out to longer wavelengths due to the expansion of the universe, a phenomenon known as redshift. The light from Population 3 stars, therefore, is largely beyond the reach of visible light telescopes. By observing in the infrared, JWST can peer back in time and study galaxies that formed just a few 100 million years after the Big Bang. In doing so, it may provide direct evidence of Population 3 stars, or at least their effects on the universe. While the hunt for Population 3 stars is still ongoing, astronomers have been able to simulate what these stars might have looked like using advanced computational models. These simulations consider the conditions in the early universe, including the lack of heavy elements and the influence of radiation and gravity. The result is a picture of stars that were much more massive than the ones we see today. In fact, it is believed that Population 3 stars could have had masses ranging from 100 to 1,000 times that of the Sun. Their extreme mass meant that they had incredibly short lifespans, burning through their fuel at a furious rate. This rapid consumption of fuel is part of the reason why these stars were so short-lived, likely only existing for a few million years before exploding in supernovae. The supernovae of Population 3 stars would have been among the most powerful events in the universe. The explosion of a star 100 times the mass of the Sun releases an enormous amount of energy, enough to outshine entire galaxies for a brief period. These supernovae not only marked the death of individual stars but also had a profound impact on the surrounding universe. The shockwaves from the explosion would have triggered the formation of new stars, pushing gas and dust together in a way that allowed for the creation of more complex structures. The heavy elements released in the explosion would have also been spread out across vast regions of space, enriching the interstellar medium and providing the necessary ingredients for the next generation of stars. Population 3 stars are often associated with what's known as the cosmic dawn, the period in the universe's history when the first stars and galaxies formed. This era is crucial for understanding the overall evolution of the cosmos, as it represents the transition from a universe that was mostly dark and devoid of stars to one that began to shine with the light of countless galaxies. The light from these first stars, as well as their explosive deaths, would have been responsible for reionizing the universe, a process in which the hydrogen gas that filled the universe was ionized by the intense ultraviolet radiation from these early stars. This ionization allowed light to travel freely through space, enabling the universe to become transparent to radiation for the first time in its history. One of the most intriguing aspects of Population 3 stars is their potential connection to black holes. Some of these stars may have been so massive that, instead of exploding in a supernova, they collapsed directly into a black hole. These black holes could have grown over time, accumulating mass from the surrounding gas and dust, eventually becoming the supermassive black holes that are found at the centers of galaxies today. The process by which black holes form in the wake of Population 3 star deaths is still not fully understood, but it is an area of intense study. The connection between the first stars and the formation of black holes is one of the key unresolved mysteries in cosmology. Despite the challenges in studying Population 3 stars directly, their legacy continues to shape the universe. The elements they created are present in every star, planet, and galaxy that came after them. These elements are the building blocks for everything we see today, from the formation of planets to the emergence of life. Without the deaths of Population 3 stars, the universe would have remained a dark and lifeless place, devoid of the complexity and diversity that we now observe. In the future, as telescopes like JWST and other advanced instruments come online, we may finally get a glimpse of these first stars and gain a deeper understanding of the universe's origins. But even without direct observations, the study of Population 3 stars has already provided us with invaluable insights into the early history of the cosmos. The first generation of stars set in motion the processes that led to the creation of everything we know. From the formation of galaxies to the creation of the elements essential for life, Population 3 stars played a crucial role in shaping the universe as we know it. As we continue to unravel the mysteries of the early universe, one thing is certain: the first stars will always hold a special place in our understanding of the cosmos. They were not just the first lights in a dark and empty universe. They were the creators of the very elements that would go on to form everything that followed. The legacy of Population 3 stars lives on in every star we see today, every planet that orbits around them, and every life form that calls those planets home. The discovery of Population 3 stars is more than just a scientific curiosity. It is an essential key to understanding the most fundamental questions about the cosmos. The question of where we come from, how the universe evolved, and why we are here, all lead back to those first stars. These stars are the original architects of the universe's chemical makeup, and their contributions laid the foundation for the formation of galaxies, planets, and life itself. Understanding them means peeling back the layers of cosmic history, starting from the very beginning of time. What is especially fascinating about the first generation of stars is that they were not just larger and hotter than anything we see today. They were fundamentally different in the way they formed and lived. These stars were born in a very specific, very unique environment. Unlike modern stars, which are made of hydrogen, helium, and heavier elements, which are the product of previous generations of stars, Population 3 stars formed when the universe was almost entirely composed of hydrogen and helium. This lack of heavier elements profoundly influenced the process of star formation. Without metals, elements heavier than hydrogen and helium, the typical cooling processes that occur in star formation were not available to regulate the temperature and pressure within gas clouds. In a universe made up only of hydrogen and helium, stars were forced to form in a very different way. The gas clouds that collapsed under gravity to form these stars would have been much hotter and denser than the clouds we see today. The stars that formed from these clouds would have been incredibly massive, as large as 100 times the mass of our Sun. These supermassive stars were the natural consequence of a universe in which the cooling effects of metals were not yet present to slow down the process. The short lifetimes of Population 3 stars, only a few million years, are another fascinating feature. The fact that these stars lived such brief lives means that their deaths were extraordinarily violent. These stars burned through their fuel at an astounding rate, reaching extreme temperatures and pressures at their cores. The end of a population 3 star's life was marked by a massive explosion in the form of a supernova, sending shockwaves and heavy elements out into the surrounding space. These elements were the building blocks for the next generation of stars and galaxies, enriching the universe with the raw materials necessary for the formation of planets and life. Despite the challenges in detecting these stars directly, astronomers are able to study their effects by observing the early galaxies and cosmic structures that were influenced by population 3 stars. These galaxies, though far away, offer a glimpse into the past of our universe. As light from these distant galaxies travels toward us, it takes billions of years to reach Earth, providing us with a snapshot of the universe as it existed in the distant past. By studying the light that these galaxies emit, astronomers can infer the properties of the stars that formed within them, including the potential influence of population 3 stars. The study of these early galaxies also provides insights into the formation of supermassive black holes. The connection between population 3 stars and black holes is an area of active research, and it is believed that some of the most massive black holes in the universe may have formed directly from the collapse of population 3 stars. These black holes would have been much smaller than the supermassive black holes we see today but could have grown over time by accumulating mass from the surrounding gas. Understanding how these black holes formed in the early universe is crucial for understanding the evolution of galaxies and the universe as a whole. In addition to the role of population 3 stars in the formation of galaxies and black holes, their influence extends to the creation of the first planets. As the heavy elements produced by population 3 stars spread throughout the universe, they created the building blocks for the formation of planets. The process of planet formation requires a variety of elements, including carbon, oxygen, nitrogen, and metals, all of which were produced in the explosions of the first stars. Without the death of these early stars, the material needed for the creation of planets like Earth would not have been available. The heavy elements they produced are the same elements that make up the Earth and all life on it. The concept of cosmic chemical evolution is central to our understanding of the universe's history. The early universe was a sterile, lifeless place, consisting almost entirely of hydrogen and helium. The first stars began the process of transforming this simple mix of elements into the complex array of elements that we see today. These stars acted as cosmic factories, forging heavier elements in their cores through nuclear fusion. When they exploded as supernovae, these elements were scattered throughout the universe, enriching the interstellar medium and making it possible for the next generation of stars and planets to form. The evolution of the universe's chemical composition is intimately tied to the life cycle of stars, and population 3 stars were the first to set this process in motion. Another exciting aspect of the study of population 3 stars is the possibility that they may have been the birthplace of the first generation of life. Although we have not yet discovered any definitive evidence of life beyond Earth, the heavy elements produced by population 3 stars are the same elements that form the basic building blocks of life as we know it. If life did exist elsewhere in the universe, it is likely that it would have been based on the same elements that were scattered by these first stars. In this sense, the death of population 3 stars may have set the stage for the eventual emergence of life in the universe. As we continue to explore the early universe, we are faced with a multitude of mysteries. The nature of population 3 stars, their formation, their short lifespans, and their contributions to the cosmic chemical inventory are just a few of the many questions that remain unanswered. But with the advent of new technologies and the launch of advanced space telescopes like the James Webb Space Telescope, we are getting closer to uncovering the secrets of these enigmatic stars. In the coming years, astronomers hope to detect the faint traces of these stars in the distant reaches of space, offering a glimpse into the birth of the universe itself. As we continue to push the boundaries of our knowledge, one thing is certain: the story of population 3 stars is far from over. Every discovery, every breakthrough, brings us closer to understanding the origins of the universe and our place within it. The first stars were not just the beginning of light, they were the beginning of everything we know. They created the elements that made life possible and laid the foundation for the formation of the galaxies, stars, and planets that would follow. In many ways, the universe we see today owes its existence to the birth, life, and death of those first stars. Their legacy lives on in every star that shines in the night sky, every planet that orbits around them, and every life form that calls those planets home. As we delve deeper into the cosmic history, it becomes evident that the study of population 3 stars isn't just an academic pursuit. It's a journey to uncover the fundamental building blocks of the universe. These stars are, in essence, the progenitors of everything that exists today. Without them, the galaxies, black holes, and even life itself might never have emerged. Understanding how these first stars formed and evolved offers insights into the very nature of cosmic evolution. But what makes them truly intriguing is not just their birth or death. It's their role in shaping the universe as we know it, in ways that continue to be revealed with every passing discovery. The first stars, made solely of hydrogen and helium, were likely much hotter than any star we observe today. Their intense heat and pressure allowed them to burn through their fuel at a much faster rate, contributing to their relatively short lifespan. These stars could have lived as briefly as just a few million years, an eye blink in cosmic terms, before exploding in supernovae. Yet, in that brief existence, they played an unimaginable role. Their deaths spread the first heavy elements across the cosmos, elements like carbon, oxygen, and iron, ushering in a new era of cosmic chemistry that would eventually lead to the formation of complex molecules and, potentially, life. But how do we study something as ancient as population 3 stars, especially since they no longer exist in the observable universe? It's a question that has puzzled astronomers for decades. While no direct observations of population 3 stars have been made, due to their faintness and the immense distances between us and these early stars, scientists have developed ingenious methods to detect their presence indirectly. One approach involves observing the oldest galaxies and the faintest stars within them, searching for traces of the signature elements that these ancient stars left behind. By studying the light emitted by distant galaxies, astronomers can infer the characteristics of the stars that formed them, including the potential influence of population 3 stars. The existence of population 3 stars is not just important for understanding stellar evolution, but for grasping the broader narrative of how the universe itself took shape. In the early stages of the universe, shortly after the Big Bang, the cosmos was filled with only hydrogen and helium, along with a few trace amounts of other elements. These two gases are the simplest and lightest elements in the periodic table. Stars formed from this primordial mixture would have been vastly different from those that formed later, as they lacked the heavier elements that allow for more stable star formation. In such an environment, the formation of stars was driven primarily by gravity, pulling together vast clouds of hydrogen and helium gas. These clouds collapsed under their own weight, heating up as they contracted. The lack of metals in the clouds meant there was no effective way to cool them down, allowing for the formation of extremely large stars. These stars would have been immensely hot, several times hotter than the Sun, and incredibly massive, many times more massive than modern stars. Their sizes ranged from 100 to even 1,000 times the mass of the Sun. But despite their immense size, they lived short lives, burning through their hydrogen fuel at an incredibly rapid rate. When these stars finally reached the end of their lives, they exploded in colossal supernovae, scattering their heavy elements far into the universe. These explosions were not just spectacular, they were essential for creating the elements that would form the building blocks of later stars, planets, and life. As the dust from these explosions spread out into the interstellar medium, it enriched the cosmos with the first generation of metals, elements like carbon, oxygen, and nitrogen, that would go on to form the next generation of stars. The explosion of a population 3 star, while short-lived, was a critical event in the ongoing process of cosmic evolution. These supernovae were not just important for the creation of heavier elements, but they also provided the necessary conditions for the formation of galaxies. The shockwaves from these explosions would have triggered the collapse of nearby gas clouds, leading to the birth of new stars. These new stars, in turn, would go on to form the first galaxies. In this way, population 3 stars acted as the catalyst for the formation of the first large-scale structures in the universe. Without their death and the resulting shockwaves, the universe as we know it would have taken much longer to form. One of the key challenges in understanding population 3 stars lies in their incredibly high masses and luminosities. The more massive a star, the brighter and hotter it burns, making these early stars incredibly luminous. However, their immense brightness also means that they are difficult to detect today. As the light from these stars traveled across the universe, it was stretched by the expansion of space, and by the time it reached Earth, it had been diluted, making it much harder to spot. This is why studying these stars indirectly, by observing the impact they had on their surrounding environment, is so important. A promising avenue of research is the study of galaxies in the early universe, distant galaxies that formed just a few 100 million years after the Big Bang. These galaxies likely contain population 3 stars, and by studying their light, astronomers can infer the presence of these first-generation stars. In particular, the James Webb Space Telescope, which is designed to observe the distant universe in infrared light, may provide a breakthrough in our understanding of population 3 stars. By detecting the faint glow of galaxies that existed during the cosmic dawn, and analyzing their chemical compositions, scientists hope to uncover more about the stars that shaped the early universe. Population 3 stars also hold significance when it comes to the formation of black holes. Supermassive black holes, which reside at the centers of most galaxies, likely began as much smaller black holes formed from the collapse of population 3 stars. These early black holes, although smaller than their modern counterparts, would have had a significant impact on their surrounding galaxies. As these black holes grew, they would have accumulated gas from their surroundings, eventually reaching the size and mass we observe in supermassive black holes today. The study of population 3 stars and the black holes that may have formed from them could provide important clues about the origins of these enigmatic objects. Furthermore, the heavy elements produced by population 3 stars are not just essential for the formation of new stars and planets. They are also the foundation for the complex molecules required for life. Carbon, oxygen, nitrogen, and other elements, critical for the formation of life as we know it, were all created in the hearts of these stars. Without these elements, life would not have been possible. The process of stellar nucleosynthesis, which occurs in the cores of stars, is responsible for the creation of all elements heavier than helium. When these elements are scattered throughout the universe in supernovae, they enrich the interstellar medium, providing the raw materials for the next generation of stars, planets, and potentially even life. The story of population 3 stars is not just about the past, but also about the future. As our technology improves and we develop more sophisticated tools for studying the universe, we will continue to uncover new insights about these ancient stars. Their role in shaping the universe is undeniable, and their influence can still be felt in the galaxies, black holes, and stars that populate the universe today. Every discovery, every breakthrough in our understanding of population 3 stars, brings us one step closer to understanding the origins of everything: stars, galaxies, planets, and life itself. As we peer deeper into the universe, searching for answers to these age-old questions, one thing remains clear: the first stars were not just the first sources of light in the cosmos. They were the architects of the universe itself. Their birth, life, and death set the stage for everything that followed. The universe that we observe today is a direct result of their existence. Their story is our story, and their legacy is written in the very fabric of the cosmos. As we continue to explore the far reaches of the universe, the study of population 3 stars remains one of the most exciting and challenging areas of astrophysics. Each discovery brings us closer to answering the profound questions about the origins of the universe and the complex processes that shaped it. As we consider the legacy of these first stars, it's important to understand the broader context of their significance in cosmic history. The formation of the very first stars wasn't a random event. It was the culmination of a unique set of conditions that allowed these massive, primordial stars to come into existence. After the Big Bang, the universe was primarily made up of hydrogen and helium, the lightest elements that were created in the first few minutes of the universe's existence. In this early universe, there were no heavier elements like carbon, oxygen, or nitrogen, metals, as we refer to them in astronomy. These elements formed much later, in the cores of the first stars. The first generation of stars, or population 3 stars, formed exclusively from these light elements. The process of star formation during the cosmic dawn was very different from what we see today. The clouds of hydrogen and helium gas that collapsed to form these stars were much denser and hotter than what we observe in the modern universe. This dense, primordial gas lacked the metals that later stars would contain, so it didn't cool down as effectively. Without metals to cool the gas, it could collapse under gravity more easily, allowing for the formation of extremely massive stars. These stars, often several hundred times more massive than the Sun, burned incredibly hot and fast, rapidly consuming their fuel. The high mass of population 3 stars meant they underwent fusion at an extraordinary rate. These stars burned hotter and brighter than anything we can observe in the present day. The sheer amount of energy generated by their cores was unimaginable. At their peaks, these stars were likely hundreds of times more luminous than the Sun, outshining entire galaxies. But despite their immense size and energy output, their lives were incredibly short, often lasting only a few million years. Compared to the lifespan of stars today, which can burn for billions of years, this was an extraordinarily brief existence. But in that short time, they changed the universe forever. The death of population 3 stars was nothing short of cataclysmic. These stars ended their lives in supernova explosions so powerful that they outshone entire galaxies for a brief moment. The supernovae of population 3 stars were likely even more violent than those we see in modern stars. These explosions scattered the first heavy elements such as carbon, oxygen, and iron, across the universe. This process, known as stellar nucleosynthesis, was responsible for creating the building blocks of all matter in the universe. These elements would go on to form the next generation of stars and eventually planets. The heavy elements produced by these first stars didn't just enrich the cosmos, they were the foundation for the formation of galaxies, black holes, and planets. Without these metals, the universe would have remained a barren, lifeless place. The carbon and oxygen produced in these supernovae would eventually form the complex molecules necessary for life. The iron and other metals that were scattered across the cosmos would form the cores of future stars, planets, and even black holes. These elements set the stage for the formation of more complex structures, ultimately giving rise to the universe as we know it. As these population 3 stars exploded and their remnants spread out into the cosmos, they enriched the surrounding gas clouds, providing the raw materials for the formation of the next generation of stars. These second-generation stars, known as population 2 stars, were made up of a mixture of hydrogen, helium, and the metals created by the population 3 stars. These new stars were much smaller and cooler than their predecessors, but they were still incredibly important. They continued the cycle of stellar birth and death, forming galaxies and systems of stars that would later give rise to planets and life. The death of a population 3 star was not just the end of a single star, it was the beginning of a new chapter in cosmic evolution. The remnants of these stars contributed to the formation of the first galaxies. These early galaxies were composed of the second-generation stars and the gas enriched by the explosions of population 3 stars. These galaxies were the first large-scale structures to form in the universe and served as the breeding grounds for further star formation. They also provided the conditions for the creation of supermassive black holes, which are thought to have grown out of smaller black holes formed in the aftermath of population 3 star explosions. The death of these stars also had another profound consequence. It contributed to the cosmic reionization event. This was a period in the early universe when the first stars and galaxies began emitting large amounts of ultraviolet radiation. This radiation ionized the hydrogen gas that filled the universe, transforming the opaque gas into a transparent state. Reionization marked the end of the cosmic dark ages and the beginning of a more transparent universe, where light could travel freely across vast distances. Without the radiation produced by population 3 stars, this process would have taken much longer to occur, and the universe would have remained in darkness for much longer. While population 3 stars no longer exist in their original form, their legacy is still visible today. The elements they produced are found throughout the universe, in the stars, planets, and galaxies that followed. In fact, some of the oldest stars in the Milky Way galaxy, known as population 2 stars, are thought to have formed from the same materials that were created by population 3 stars. These stars serve as a living record of the early universe and provide important clues about the formation of the first stars and galaxies. The influence of population 3 stars can also be seen in the formation of supermassive black holes. The earliest black holes, thought to have formed from the collapse of population 3 stars, were likely much smaller than their modern counterparts. But over time, these small black holes grew by accumulating gas and matter from their surroundings, eventually becoming the supermassive black holes that sit at the centers of galaxies today. The study of these black holes provides valuable insight into the early universe and the formation of the first structures in the cosmos. Even though population 3 stars have long since burned out, their story is far from over. In fact, the study of these stars is still ongoing, with new discoveries being made all the time. Scientists continue to search for indirect evidence of population 3 stars, using advanced telescopes and sophisticated techniques to peer back in time to the earliest days of the universe. The James Webb Space Telescope, with its ability to observe distant galaxies and stars in the infrared, is expected to provide critical data about the first generation of stars. With its powerful instruments, scientists hope to uncover more about the birth of the first stars and galaxies, as well as the role these ancient stars played in shaping the cosmos. One of the most intriguing aspects of population 3 stars is their potential to hold the key to understanding the fundamental processes that govern star formation. These stars, formed in the earliest days of the universe, offer a glimpse into the conditions that existed when the first stars began to form. By studying these stars, scientists can learn more about the physics of star formation and the behavior of matter under extreme conditions. This knowledge could help us better understand how stars form in the modern universe, as well as how galaxies and black holes evolve over time. As we continue to explore the mysteries of the universe, population 3 stars remain one of the most fascinating and enigmatic subjects of study. These first stars were the architects of the universe, shaping the cosmos in ways that continue to reverberate through space and time. From the formation of galaxies to the creation of the elements necessary for life, the legacy of population 3 stars is woven into the very fabric of the universe. Their birth, death, and the cosmic processes they set in motion continue to influence the universe today. As we peer into the depths of space, we are not just looking at the past. We are witnessing the ongoing story of the universe and the stars that created it. As we continue to probe deeper into the mysteries surrounding population 3 stars, one aspect that remains particularly fascinating is the sheer scale of their impact on the cosmos. The early universe was vastly different from the one we inhabit today, and understanding how the first stars ignited the cosmic furnace of creation allows us to piece together the history of everything that followed. This is where the concept of cosmic evolution comes into play, the process by which the universe transformed from a hot, dense state after the Big Bang into the vast and complex structure of galaxies, stars, planets, and life. The early universe, in the absence of metals, was a place where star formation was governed by the basic elements, hydrogen and helium. In the first few 100 million years, the universe was a hot, dense soup of particles. These conditions prevented the formation of stars as we know them today. The absence of heavier elements, which in modern star formation play an essential role in cooling the gas clouds and initiating gravitational collapse, meant that star formation could only occur through mechanisms entirely different from those we observe today. Instead of slowly cooling and contracting, the hydrogen gas in these early clouds would collapse rapidly due to the immense pressures and temperatures. This rapid collapse led to the formation of massive, short-lived stars. These stars could reach hundreds of times the mass of the Sun, burning hot enough to trigger nuclear fusion at a rate that would exhaust their fuel in just a few million years. Their rapid life cycle, birth, burn, explode, was a stark contrast to the slower, more stable evolution of stars that we observe now, such as our own Sun. The high temperatures within these stars allowed them to forge elements heavier than hydrogen and helium, creating the first building blocks of the universe's chemical diversity. One of the significant elements these stars produced was carbon, a crucial element for life. The high temperatures and pressures within population 3 stars allowed for the fusion of helium nuclei into carbon, one of the first times such an event could take place in the universe. Carbon atoms are fundamental in the formation of complex molecules and compounds, including organic compounds. This early production of carbon laid the groundwork for the eventual formation of planets and life itself, though this would not occur for billions of years. This process underscores the interconnectedness of cosmic events, how the death of these first stars was not just an end, but a pivotal beginning for future generations of stars, planets, and ultimately, life. Population 3 stars also had a profound role in shaping the future evolution of galaxies. When these first stars exploded as supernovae, they released immense amounts of energy, along with heavier elements, into the surrounding interstellar medium. This process of stellar enrichment, the creation and dispersal of elements, was key in building up the chemical richness of future generations of stars. It's a feedback loop that continues today. The gas that forms new stars is progressively enriched with heavier elements, which in turn affects the types of stars that form. These early supernovae are thought to have contributed to the birth of the first galaxies, triggering the collapse of gas clouds that eventually gave rise to entire systems of stars, black holes, and nebulae. In terms of the large-scale structure of the universe, the initial generations of stars were crucial in shaping the way galaxies formed. They provided the initial gravitational seeds for the formation of larger structures, influencing the formation of early galaxies. These galaxies, often much smaller and more chaotic than the large spirals and ellipticals we see today, were populated by the second generation of stars, the population 2 stars, which were themselves enriched by the products of population 3 star explosions. But these early stars also raised the question, how did they form? What was the exact process that brought them into existence? It's here that the concept of cosmic dark matter becomes significant. Dark matter, a mysterious and invisible substance that makes up most of the mass in the universe, played a crucial role in the formation of these first stars. Though dark matter does not emit, absorb, or reflect light, and thus cannot be directly detected, it exerts gravitational forces that affect the movement of visible matter. In the early universe, dark matter was critical in helping gas clouds collapse under their own gravity, eventually leading to the formation of the first stars. These first stars were not only massive and hot, but they were also brief. Their short lives meant that their end was marked by violent supernovae, which were much more energetic than those from the stars we observe today. When they exploded, they triggered the formation of black holes. These black holes, possibly the very first supermassive black holes, had the potential to grow at incredibly rapid rates, consuming gas and merging with other black holes to form the giants that sit at the centers of galaxies today. Their formation is another piece of the cosmic puzzle, offering insight into how the largest and most mysterious objects in the universe came to be. Given how little we know about these early stars, scientists have turned to simulations and indirect evidence to uncover their secrets. Astronomers use computer models to recreate the conditions of the early universe, simulating the formation of population 3 stars and their supernovae. These simulations allow researchers to predict the kinds of stars that would have formed, their properties, and how they might have interacted with their environment. The results of these simulations are crucial in guiding future observations. In addition to simulations, astronomers are also searching for direct evidence of population 3 stars. While these stars have long since died, their light may still be detectable, albeit faintly. The James Webb Space Telescope, JWST, is designed to peer deep into space and look back in time to when the first stars were born. By detecting the faint glow of these early stars and galaxies, astronomers hope to gain insights into the formation of the first stellar populations. Webb's infrared capabilities are particularly useful because they allow it to detect the light from distant objects that has been stretched into longer wavelengths due to the expansion of the universe. This will enable astronomers to study the earliest light ever emitted in the universe. In fact, the JWST has already begun its mission to uncover the secrets of the universe's earliest days. Its ability to look further into space and time than any previous telescope means that we may be on the brink of discovering the first true evidence of population 3 stars. This would be a groundbreaking achievement in our understanding of the universe and could answer questions about the very nature of cosmic evolution. The study of population 3 stars doesn't just offer insights into the past. It can also help us understand the future. By studying how these first stars formed, lived, and died, scientists can gain a deeper understanding of the processes that govern star formation and stellar evolution. The massive stars of population 3 were the progenitors of the stars we observe today. Their explosive death seeded the universe with the heavy elements necessary for the formation of planets, and ultimately, life. Without them, the universe as we know it simply wouldn't exist. Moreover, the study of population 3 stars is intrinsically linked to one of the biggest questions in astronomy: the origin of life. As we look for life beyond Earth, we must understand the conditions that make life possible. The early chemical elements formed by population 3 stars laid the groundwork for life's building blocks. Without these elements, there could be no carbon-based life, no amino acids, no DNA. In a very real sense, the first stars are part of the cosmic story of life itself. Thus, population 3 stars represent more than just distant objects from the early universe. They are the keys to understanding the very fabric of our existence. As we continue to study these stars and their explosive deaths, we inch closer to answering some of the most profound questions in science. How did the universe come to be? What are the fundamental processes that have shaped the cosmos? And, perhaps most intriguingly, are we alone in the universe, or are we part of a much larger, far-reaching story that began with the first light of the universe? The legacy of population 3 stars is one that echoes through time and space. These first stars were the pioneers, blazing a trail that would eventually lead to the formation of galaxies, planets, and life itself. The understanding of these ancient stars not only deepens our knowledge of the universe's history, but also shapes our future exploration of the cosmos. Each discovery about these stars takes us one step closer to understanding the origins of everything we see, hear, and experience, as well as the very origins of the universe itself. The study of population 3 stars continues to be a journey into the unknown, one that will surely reveal more mysteries in the years to come. As we continue to delve deeper into the mysterious world of population 3 stars, there are still many questions that remain unanswered. With each breakthrough, astronomers are uncovering more pieces of this cosmic puzzle, but much of the story of the universe's earliest stars is still obscured by the vastness of time and the limitations of current technology. However, the ongoing advancements in observational astronomy, particularly with the launch of the James Webb Space Telescope, offer us a new hope for revealing more about these ancient beacons of light. The journey to understanding population 3 stars is not just about uncovering facts. It's about learning how the entire universe came into being. The earliest stars were the first true sources of light in an otherwise dark and featureless universe. Before their formation, the cosmos was a nearly opaque fog of hydrogen and helium, with no clear structures or defined objects. These first stars were the catalysts for the universe's transformation from a primordial soup into the complex web of galaxies, stars, and planets we see today. Through their violent births and deaths, these stars enriched the universe with the very elements that make life possible. Carbon, oxygen, nitrogen, and iron, elements critical to life as we know it, are the legacy of these ancient stars. Without their explosive supernovae, which scattered these elements across the universe, the conditions necessary for planets and life would never have come to pass. One of the most exciting aspects of studying population 3 stars is how they might inform our understanding of the formation of supermassive black holes. These black holes, which reside at the centers of most galaxies, including our own Milky Way, are thought to have been born from the collapse of the first stars. The massive progenitors of population 3 stars, with their rapid evolution and explosive deaths, could have formed black holes with masses hundreds or even thousands of times that of the Sun. These early black holes, in turn, may have grown quickly by consuming nearby gas, eventually merging with other black holes to form the supermassive black holes we observe today. Understanding how these first black holes came into existence is a crucial part of understanding the evolution of galaxies and the large-scale structure of the universe. At the heart of this research lies the mystery of how these first stars formed in the first place. In the early universe, the primary constituent was hydrogen, with trace amounts of helium. There were no heavier elements like carbon, oxygen, or nitrogen to aid in the cooling of gas clouds, which would normally collapse to form stars. In the absence of these elements, how did gas clouds manage to collapse under their own gravity to form such massive stars? This is still a subject of intense study. It is believed that dark matter played a crucial role. The gravitational effects of dark matter could have helped these gas clouds collapse more efficiently, leading to the formation of the first stars. Yet, while this theory is compelling, it remains just that, a theory. Direct evidence for the role of dark matter in star formation is still lacking, and more observations are needed to confirm these ideas. As astronomers continue to piece together the history of these first stars, it is becoming clear that they were not only the progenitors of galaxies, black holes, and heavier elements, but also the building blocks of the future universe. They paved the way for the formation of more stable, long-lived stars like those in the Milky Way, and ultimately, they set the stage for the formation of planets and the potential for life. The birth of these stars marked the beginning of the cosmic clock, and their rapid deaths opened up the pathways for the next generations of stars and galaxies to form. It's also essential to consider the more philosophical implications of studying population 3 stars. These ancient cosmic objects are not just relics of the past, they are our link to the very origins of the universe. By studying them, we can uncover the conditions that led to the formation of our own solar system, and by extension, life on Earth. The first stars created the elements that are integral to life as we know it, and without them, we would not exist. As we look further into the past, we are not only studying the universe's history but also our own origins. The birth and death of these stars are deeply intertwined with the story of the cosmos and the story of life itself. The formation of population 3 stars also has a profound impact on our understanding of the fundamental forces that govern the universe. The conditions under which these stars formed, without the influence of metals and with only hydrogen and helium to work with, show us how fundamental forces such as gravity and nuclear fusion operate in their purest forms. These early stars were the testing ground for many of the physical laws that continue to govern the universe today. By studying them, we gain deeper insight into the physics of the early universe and how it evolved over time. While we continue to explore the legacy of population 3 stars, it's important to acknowledge the gaps in our knowledge. Despite the best efforts of scientists, there are still many mysteries that remain unsolved. For example, what was the exact mechanism that triggered the formation of these first stars? How did they evolve, and why did they burn out so quickly? How did the black holes they left behind contribute to the formation of the supermassive black holes we see today? And most tantalizing of all, could there be remnants of population 3 stars still lurking in the universe, waiting to be discovered? Answering these questions will require not only technological advancements but also new theories and models that can help us understand the conditions of the early universe. The search for population 3 stars is far from over, and with each new discovery, we come closer to understanding the nature of the universe's first light and how it shaped everything that followed. One of the challenges facing scientists is that population 3 stars likely left little direct evidence behind. These stars were massive, hot, and short-lived, and their remnants may have been absorbed into later generations of stars and galaxies. However, the light from these stars may still be detectable through advanced telescopes like the James Webb Space Telescope, which has the ability to peer deeper into the past than ever before. By looking at distant galaxies, we may be able to detect the faint glow of these early stars, helping us reconstruct the history of the universe's first generation of stars. In addition to this, we may also learn more about population 3 stars through the study of high-redshift galaxies. These galaxies, which formed only a few 100 million years after the Big Bang, may be home to the remnants of population 3 stars. The light from these galaxies, stretched by the expansion of the universe, could reveal important clues about the properties and life cycles of these first stars. By studying the chemical composition of the gas in these galaxies, astronomers hope to uncover traces of the elements produced by population 3 stars and learn more about the role they played in shaping the universe. As we continue to look further into the past and study the remnants of population 3 stars, it becomes clear that our understanding of the universe's earliest days is still in its infancy. The journey to uncover the secrets of the first stars is one of the most exciting and important challenges in modern astronomy. With each new discovery, we come closer to understanding the origins of the universe and our place within it. The story of population 3 stars is the story of the universe's beginning. They were the first beacons of light in a dark and empty cosmos, and their legacy can still be seen today in the stars, galaxies, and planets that fill the universe. The study of these stars not only helps us understand the universe's past but also guides us in our quest to understand its future. As we continue to explore the mysteries of the cosmos, we are uncovering the building blocks of everything that exists, and in doing so, we are discovering the true story of the universe itself. As we continue to explore the profound legacy of population 3 stars, we are confronted with the vastness of the questions that remain unanswered. These first stars were fundamental in shaping the universe, and understanding them can lead us to greater insights into the very fabric of space and time. The exploration of these ancient celestial bodies is an ongoing scientific effort that demands more than just the detection of light from distant galaxies. It calls for a deeper comprehension of the processes that shaped the universe from its earliest moments. The process of star formation in the early universe is fundamentally different from what we observe today. In the present-day cosmos, stars form from molecular clouds of hydrogen, helium, and heavier elements, where gravity causes the gas to collapse under its own weight, eventually igniting nuclear fusion. However, in the primordial universe, there were no metals, elements heavier than hydrogen and helium, that could help cool the gas clouds and aid in the collapse. This is a significant challenge, as it was believed that such clouds should remain too hot to collapse without the presence of these metals. This absence of metals in the first few 100 million years after the Big Bang means that population 3 stars were likely born from a much different process than the stars we see around us today. The exact details of how the first stars formed remain a subject of intense research. One of the leading hypotheses suggests that dark matter played a critical role in the collapse of these early gas clouds. Dark matter, which interacts through gravity but not electromagnetically, would not have been affected by the lack of metals in the gas clouds. As a result, it could have provided the additional gravitational pull necessary to trigger the collapse of the gas, forming the first stars. This theory, while compelling, is still a topic of debate, and further observations are needed to confirm the role of dark matter in the star formation process. Despite the lack of metals, the first stars were extraordinarily large. Population 3 stars are theorized to have been much more massive than modern stars. While the average star in the present-day universe is only a few times more massive than the Sun, early stars may have been hundreds, even thousands, of times more massive. This huge mass would have led to their rapid life cycles, burning through their fuel at an accelerated pace. These massive stars burn much hotter and faster than their modern counterparts, meaning that their lifespans were incredibly short, typically only a few million years. While these stars existed for only a brief moment in cosmic time, their impact on the universe was enormous. They generated intense radiation, which began to reionize the gas in the universe and helped to create the large-scale structure of the cosmos. One of the most striking aspects of population 3 stars is their rapid death. Because these stars were so massive, their fuel was exhausted quickly, and they ended their lives in violent supernovae explosions. These explosions were not like those of modern stars. They were far more energetic and left behind black holes of extraordinary mass. These primordial black holes are thought to be the seeds from which the supermassive black holes at the centers of galaxies could have formed. In the aftermath of a population 3 star's death, the explosion would have scattered heavy elements into the surrounding space, enriching the universe with the materials needed for the formation of future generations of stars and galaxies. These heavy elements, such as carbon, oxygen, nitrogen, and iron, are the building blocks for planets and life. Without the violent deaths of these first stars, the conditions for life as we know it could never have existed. The remnants of population 3 stars are likely to be incredibly difficult to detect. These stars were so massive and short-lived that they left little behind. The supernovae they caused would have scattered their elements into the surrounding universe, but the exact locations of these remnants are still largely unknown. Furthermore, the very nature of these stars, their massive size and rapid evolution, means that they likely existed in a very different part of the universe than we are used to observing today. Early galaxies, where population 3 stars formed, were much smaller and more compact than the galaxies we see now. These galaxies were also much more distant, which means that detecting them through current technologies is an immense challenge. The advent of advanced telescopes, particularly the James Webb Space Telescope, JWST, offers hope in uncovering these elusive remnants. With its ability to observe the universe in the infrared spectrum, the JWST can peer further back in time than ever before. It will be able to observe the light from some of the first galaxies that formed after the Big Bang, potentially revealing signs of population 3 stars. The JWST may also be able to detect the faint traces of their explosions, helping to identify the locations of these ancient stars and their black hole remnants. While the search for population 3 stars is still in its infancy, astronomers are optimistic that new data from the JWST, along with other advanced observatories, will help to uncover more about these cosmic pioneers. The JWST will enable astronomers to observe galaxies that formed just a few 100 million years after the Big Bang, providing a window into the earliest stages of the universe. These observations could reveal important information about how the first stars formed and how they influenced the evolution of galaxies and black holes. In addition to the observational breakthroughs, theoretical work continues to refine our understanding of population 3 stars. Computer simulations that model the formation and evolution of these stars are becoming more sophisticated, incorporating new theories about the role of dark matter, gas collapse, and the effects of cosmic radiation. These simulations help to create predictions about what we might expect to observe, guiding future observational efforts. It's not just the science of population 3 stars that is fascinating, but also the philosophical implications of their existence. These stars are the ultimate symbols of the beginning of everything. They are the first lights in the darkness, the seeds of everything that followed. They are, in a very real sense, the ancestors of all that exists. Without them, there would be no galaxies, no stars, no planets, and no life. By studying them, we are learning not only about the history of the universe but also about our own place in the grand cosmic scheme. The first stars made us possible, and in understanding them, we understand the origins of our existence. The story of population 3 stars is still being written. Each discovery, each observation, brings us one step closer to unraveling the mysteries of these ancient cosmic objects. We are uncovering not only the birth of stars but the birth of the universe itself. The first stars are the key to understanding how the universe evolved, how galaxies and black holes formed, and how the very elements that make life possible came into being. As we continue our search for these cosmic ancestors, we are not just looking for stars. We are looking for the answers to some of the most profound questions about the origins of everything we know. The mysteries surrounding population 3 stars are so vast that each new discovery deepens our appreciation of the complex processes that led to the universe we know today. These early stars were not just the first sources of light in the cosmos. They were the architects of the first significant chemical elements in the universe. Before their creation, the universe consisted almost entirely of hydrogen and helium, the lightest elements that were formed in the first few minutes following the Big Bang during a process called Big Bang nucleosynthesis. But it was the death of population 3 stars, through supernovae or perhaps even direct collapse into black holes, that produced the heavier elements we now find in abundance throughout the universe, such as carbon, oxygen, and nitrogen, elements essential to life as we know it. The rich chemical soup created by these stars was the building block for future generations of stars, planets, and galaxies. It is believed that population 3 stars enriched the intergalactic medium with metals, or elements heavier than hydrogen and helium, by expelling their contents into the surrounding space in the form of supernovae explosions. These explosions would have been incredibly energetic, dispersing these metals throughout the cosmos. Over time, these enriched regions of the universe would have led to the formation of the first galaxies, which were populated by stars that had higher metallicity than the first-generation stars. One of the most intriguing aspects of these first-generation stars is their role in the process of reionization. Around 400,000 years after the Big Bang, the universe had cooled enough for atoms to form, primarily hydrogen and helium. During this recombination era, the universe was filled with neutral gas, and light could travel freely. However, as the first stars began to form, their intense ultraviolet light ionized the surrounding hydrogen gas, making it opaque to certain wavelengths of light. This process, known as reionization, marks a critical point in the evolution of the universe. The intense radiation from population 3 stars helped to transform the early, dark universe into a more transparent one, allowing light from subsequent generations of stars and galaxies to travel freely across vast distances. Understanding reionization and the contribution of population 3 stars to this process is a critical area of research. The study of reionization is not only important for understanding the early universe but also for understanding the conditions that led to the formation of galaxies. Reionization is thought to have begun around 400 million years after the Big Bang, but the exact timeline and the role of population 3 stars in this process are still unclear. Did these early stars provide the necessary radiation for reionization, or was the process mainly driven by later generations of stars? Could population 3 stars have been more widespread and long-lived than currently thought, playing a more central role in the reionization epoch than we realize? As astronomers continue to search for evidence of population 3 stars, the discovery of their remnants or signs of their existence will provide crucial answers to these questions. The James Webb Space Telescope, JWST, launched in 2021, is expected to play a pivotal role in this quest. Its powerful infrared capabilities allow it to peer deeper into the universe's past than any previous telescope. By observing the first galaxies and the light emitted by the earliest stars, the JWST might provide direct evidence of population 3 stars, their explosions, and their contributions to the universe's evolution. The search for population 3 stars also involves looking for indirect signs of their existence. For example, astronomers are studying the absorption lines in the spectra of distant quasars to understand the properties of the intergalactic medium. The metal content in these absorption lines can provide clues about the enrichment of the universe by the first stars. Additionally, astronomers are looking for unusual patterns in the cosmic microwave background (CMB) radiation, which might reveal signatures of the first stars and the reionization process. Any evidence of the first stars, whether direct or indirect, will help to piece together the puzzle of the early universe and provide a clearer picture of the conditions that led to the formation of the galaxies, stars, and planets we observe today. But the mysteries of population 3 stars extend beyond their role in cosmic evolution. They also challenge our understanding of stellar evolution itself. These stars were unlike anything we see today. Modern stars form in clouds of gas that have been enriched with elements heavier than hydrogen and helium. These metals serve to cool the gas, allowing it to collapse into dense regions that eventually ignite nuclear fusion. But in the case of population 3 stars, the absence of metals meant that the formation process had to be fundamentally different. Without the cooling effect of metals, the gas clouds from which these stars formed were much hotter than those in the modern universe. As a result, the first stars may have formed in a different way, perhaps more rapidly and under different conditions than we can observe today. The lack of metals also meant that population 3 stars were more likely to be massive than the stars we see today. Modern stars, like our Sun, typically have masses ranging from a fraction of the mass of the Sun to several times its mass. But the first stars were likely hundreds or even thousands of times more massive. These stars would have had much shorter lifespans, burning through their fuel in just a few million years, compared to the billions of years of life for stars like the Sun. Their rapid evolution also meant that they were likely to end their lives in spectacular fashion, either as hypernovae, producing black holes, or as very energetic supernovae, leaving behind neutron stars or black holes. The discovery of these first-generation stars will not only shed light on the formation of stars and galaxies, but will also provide insights into the extreme conditions under which they formed. Understanding how stars can form without the usual cooling mechanisms, and how they can reach such extreme sizes is essential for understanding the broader processes of cosmic evolution. As we continue to develop more advanced observational tools and improve our theoretical models of stellar formation, we are likely to uncover more about the mysterious origins of the first stars and their impact on the universe. Perhaps one of the most exciting aspects of studying population 3 stars is the potential for new discoveries that could radically change our understanding of astrophysics. These stars may hold the key to understanding the nature of dark matter, as their formation and evolution could be influenced by dark matter in ways that we have yet to fully comprehend. They also raise fundamental questions about the nature of the universe itself. How did the first stars form? What conditions were necessary to create the universe as we know it? What role did these early stars play in the formation of galaxies, black holes, and other cosmic structures? As the search for population 3 stars continues, we are on the brink of discovering new and profound insights into the origins of the universe. These stars represent the beginning of everything that followed in the formation of galaxies, stars, and planets, and eventually, the conditions necessary for life. By studying them, we are not just uncovering the story of the universe's past, we are also learning about the deep and mysterious forces that govern the cosmos. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.